Okay, so we start off this live coding where we finished the last one. So in the last one, we covered sort of the aluminum pre-processing steps. Open that in a new window. And here we read in the data. We did the cleanup, the enhancement, the segmentation, and then extracted all of the bubbles. And finally, saved all of the bubbles that we could track as a CSV file. We then have an animation. We have the CSV file here with all the columns and values in it. We also have a JSON file, which has the same data in a slightly more structured format, where we can see area, and then each of the bubbles, and everything else inside. The preview doesn't work particularly well because there's so many elements that we're trying to track. And so here we just focus on, just have to refresh. Oh, there we see it. And finally, we have the sort of animation that we made where we can see the bubbles over a number of different frames. So we can see how the bubbles move over the course of the experiment. And here we just show the largest bubbles, and sort of the red indicates the full path that they have. We see that there's quite a few that appear and disappear again, and so we'll have a number of challenges to deal with tracking them. And so now what we can do is we click on the output and we can make a new kernel from this output. So by clicking new kernel, we'll get a new kernel, which will give us that as a starting point. So here we can just basically, you'll get a kernel like this when you start. I might have to restart session for whatever reason. Kaggle seems to be struggling today. Again, we'll have a lot of the unit testing code in here. So we make this little function called autotest, which checks to see if there's any tests in our code and runs them. This is very good practice to make sure that your code works and that each function sort of works well on very simple, small cases. For tracking, this is particularly important because we want to ensure that when we're tracking a bubble, that it does what we expect it to do with very simple scenarios with just two bubbles, for example. And so here we have some helper functions that we work on. The first one is just called flattendict, and this just kind of flattens out all of the data that we have. If you're interested, you can look at this in more details. There's a little bit of documentation here as well as some tests. So when we define it, we can see that the function works and everything gives us sort of the right results. We now can sort of load the data that we saved last time. And so we have 11,000 bubbles that we load in, and we have all of the shape analysis information for them. And so because we saved it as JSON, we're actually able to get sort of structured information about each bubble. And so here we have the bounding box, which is a little array that has sort of the upper left, bottom right corners. We have the slice, so the exact kind of region, very similar to bounding box, but it's a little easier to use on the image itself, centroid, and everything else. So we can now kind of preview this again. And what we show here is we take the bubbles that are larger than 50, so 50 pixels in size. We sort them by the timestamp in milliseconds because we added the timestamp from the video to it. And so here we keep 10 frames with bubbles. And so what we do is we, keep 10 frames with more than 10 bubbles inside the frame. And so here are all sort of the many bubble frames, and these are basically big bubbles grouped by the timestamp. For each timestamp, we count the number of bubbles that we have, and then we keep the ones with more than 10. And so here we can say big bubbles are kind of any frame that's in one of these, and then we can show that many bubble frame as a result. And what's quite nice about that is that we can make a plot, and rather than seeing everything that's going on, we can just focus on frames that have large bubbles and more than 10 of them, and we take sort of these 10 consecutive. So between 6.1 milliseconds and 6.65, we sort of have these different views. We can also change the plot function to make it slightly more transparent. We use alpha equals 0.5. It should be a little bit easier to see sort of the tracks that these bubbles are taking. But you can see that sort of the paths of the bubbles are quite easy to follow here. So now what we do is we pick just 2 good frames. So we sort of have a before and after and try to see how well we can track that. So rather than trying to track on the whole experiment at once, we focus on tracking on just sort of a short little bit of work. And so here, what we'll use as our first sort of starting point is this nearest neighbor tracking routine. So I've sort of pre-coded all of this because it's a little bit tricky to get right. If we go back to the dynamic experiments lecture, you can see some of the basic code for this implemented as separate pieces. So if we go down to dynamic experiments, lecture handout, we can see a lot of the tracking code done. Sort of nearest neighbor for row in frame 1, for row in frame 2. We calculate the distance, we plot the distance, and then we kind of show this result. And so we do very much the same thing in the code, and then we have these sort of animations like we did before, but now we don't show any of these animations. This is just sort of implicitly done as the code runs. And so it does all of these comparisons from one frame to the next frame, and then we take the nearest one and work with that more. And so if we go back to here, we sort of have the last row, the current row, the maximum distance, and so here we say this is as far apart as the points can be and sort of still be counted. If we include all of the points from the last row, and so this is kind of the question if you want to keep the points from before, even if you don't see it in the next row. And so if a bubble disappears, assume it's in the same spot. If you do false, if a bubble disappears, assume it's really gone. That's sort of the output type. Status means add a status flag to each bubble. And so this lets us see if there's a new bubble, if the bubble was removed, or if the bubble was just propagated forward because it couldn't be found. Maxdim is the dimensions. And so this function is written sort of very generally so that it works on 2D, 1D, 2D, or 3D points. Right now it's set up for 3, but when we apply it, we'll run it on 2. And then you see here, one of the things we briefly mentioned are sort of these type annotations. And so these can be quite helpful to add to functions. So if you look at tools like MyPy, you can learn more about this. But basically, this makes Python a little bit more serious of a programming language, better suited for larger projects, and it's also a little bit easier to learn because when you have all these annotations, you kind of know what comes in and know what goes out. And so here we see that the output is a dictionary of strings and lists of floats. And so it's sort of these key values that we had talked before, that you kind of give it in an input that's dictionary, string, floats, for the last row, the current row, and it basically gives you the tracking between them as an updated current row. And so here we have kind of simple examples that if you just have a of x000 and your last frame has nothing in it, then you match nearest points basically just gives you a back. So what you'd kind of expect. If you match a to a, then you'll see that it renames a to x. And so that's the first point that's matched. You can then match a to x of 1, 1, 1, and you'll see that you have a xb. So it didn't match those points because they're too far apart. And then we can start tweaking this, and you kind of see a number of different examples. Ultimately, the last examples start to look a lot more kind of realistic, but we'll start off with just simple problems. And so here we see that it works. We then have this simple little function to kind of turn each row that we have into a dictionary. And so what this does is take the XYZ coordinates or XY coordinates for all the points in a frame and sort of spit them out as a list, as a dictionary where each one of the points is a string. So that's the key of the list, and the value is then the position of that. And so since it's only 2D, the value is then sort of the x coordinate and then the y coordinate. And so we see that this frame, we have the timestamp here, we have the label of that point, and then we have the coordinate. You might ask yourself sort of why these labels are kind of so random. How come it's not 1, 2, 3, 4, 5, 6 or sort of continuous labels? And the reason for that is because we've only kept the points that were above 50 pixels. And so a lot of the points below 50 pixels have been, or all of them have been removed. And a lot of them had IDs like we can see here, 0.1 and 0.2 had that ID. 0.3 did not, 0.4, 0.5, 0.6, all the way to 0.13 also were too small, and then they got big enough again. And so here we see that there's sort of that filtering that's going on, which makes the label itself not particularly meaningful. And so we'll give them new labels when we run this matching. And so now what we want to do is track sort of from frame 1 to frame 2. So we had these very simple points of frame 1 to, and frame 2 that we showed up here. Sort of the before and after, the red and the blue points. And now what we can do is we can test this function on sort of a fairly simple case. And so we change the max distance to 50. So this is now 50 pixels apart. It used to be 0.01. Clearly that's too small. We want to allow for some movement in our system. And the max dimension's 2, and to add status. And so what we can do here is see which points we were able to track, which points are new. So the M and N point are new. It didn't see them before. This point it couldn't find sort of a follow-up for. So even though it showed up in the first frame, it doesn't know where it ended up in the last frame. And so that works fairly well. If we change this maximum distance to 1e minus 3, we'll see that almost none of the points get tracked. So all the points in the first one aren't found in the next one, and all the points in the next one are just added on to the first one. And so here, no effective tracking was done. If we then change this to 1,000, we'll see that kind of every point gets tracked. So there's no points that weren't able to find a match in the next slide, but of course there were still points that were in the next one that were not in the previous one. And so tweaking this number till we get sort of the right balance of inputs and outputs is quite important. So 25 and 50 gave us more or less the same number. And that's what we use. So now we can do this cumulative matching of points, where rather than matching points for just 2 frames, that we sort of go through all of the frames and try to track everything through it. So here we can do this cumulative matching. We now can start showing this, so we see all the different points that we tracked. And we can start making plots. And so we can focus on what status each bubble has and start seeing these were the paths of the bubbles that we tracked, and that's how they moved throughout the frames. So where you see these paths start are where the bubble kind of entered the scene. So before that, there was no bubble in that position. Here you see bubbles and then where they stopped. And so occasionally we'll see ones that start and stop again, but that tends to be more the exception than the rule. We can also see sort of the movements What's quite interesting is we see the frames where kind of everything jumped at the same time. So here there's sort of a large jump down in this direction, and what that probably means is that it's not actually the bubbles suddenly moving quickly, it's the frame of reference suddenly moving quickly. And sort of the small movements are probably much more relevant for us than the big movements. So we can kind of tweak our plots even more and start to see how much, what was the delta in movement at each time frame. So how large were the jumps? And most of the jumps were fairly small, but there were certain frames where things moved quite a bit. We can then process that a little bit more so that we get sort of the vectors of movement for each point. We sort of add those on as additional columns. And now we can look at like the distribution of those vectors. And so we can see which vectors, how far each bubble moved at every given point, and exactly what kind of distribution that was, because that also lets us maybe filter and group together the points better. This plot takes a little while to show because there's lots of points that it's got to go through. But when it finishes running, and we can also sort of cheat and just go to the output directly. So commit to make sure our notebook gets sort of submitted and run again. And here we can go down and see the distribution of this so that we can see that sort of the jumps in X are fairly standard, and the jumps in Y, most of the points really don't move very much, but then there's a few frames where there's very large changes. And so that covers sort of the next part of the tracking experiments.